Hello everyone. In today's video, I will show you step by step how to perform a static analysis, a short but comprehensive analysis using the Abaqus user interface. I will try to explain the basics of each module in Abaqus while setting up the analysis. So let's start. The first thing that we have always do is to define the working directory in Abaqus, to choose the folder where all the generated files from the analysis will be saved in. So now, most case engineers import the CAD geometry from a CAD software into Abaqus in several formats like step file, SAT file, but Abaqus has its own sketcher and we can create a simple 3D and 3D geometry here. Let's name it specimens 3D modeling solid, and let's make a circle, define the radius. Okay, let's make another circle, let's make it a cube and click X, done. So now let's make 500, find the depth, the length of the tube. Okay, perfect. In Abaqus, units are not displayed anywhere in the interface. So this means that you must always keep your units consistent through the entire analysis. So you can advise this table for the unit consistency, and we're using millimeters, SI millimeters, and this is the unit for the length, and this is the unit for other quantities during analysis. Next, we have to define a material, to create a material. Let's make a Mandurin material, and for a static analysis, for a linear elastic analysis, the only parameters that we need is the Young modulus and the Poisson ratio. The Young modulus in terms of megapascals, so if it's 70 gigapascal, this value shall be 70,000 megapascals. In the scalar method, 3. Okay, so next in Abaqus we have to create a section based on this material, and for 3D solid elements, homogeneous. This material, okay, perfect, the section has been created, and now we have to assign this section in our parts. So we click this button, assign section. Our part from white color will be green now. This means that this part has an assigned section. I will make also partition. I will choose set plane 0 perfect. I will explain later why I'm doing that. Use datum planes, click create. Now you can see it. Perfect. Now we can mesh our part. These green colors mean that this is an easy geometry. We can mesh the part with structure hex mesh. Click here. Abaqus always give a default value for the global size. Let's make it 5. And this is a value tool. We have the element type for our part. Standard if we make an implicit analysis, or explicit if we use the explicit solver, and the geometry order linear, and some other options for advanced user. Let's unclick the reduced integration. Perfect. Click this button for meshing the part. Okay, everything is perfect. In Abaqus, next we have under the assembly module, we have to create the instance of our analysis, which consists of many parts. Now we have only used this part. Okay, and move forward with our step. This is static general step, static analysis. Time period 1, time is meaningless in static analysis. Non-linear geometry, in most cases, it's recommended to put it on. In our analysis, not so important. This is the field and history output, some default parameters and default quantities that Abaqus exports in the results, and we can move forward with the boundary condition. We have to create fixed supports at the ends of the tube. We have to select these faces by pressing the Shift key in the keyboard and choosing all the 4 faces. Done, and constrain all the degrees of freedom by clicking the last one in constraint. Okay, perfect. So now we have to apply some pressure on the tube for the loading. This is why I make this partition to split my tube into 2 partitions. Let's make a pressure on the upper surface. I usually use this as a pressure in terms of total force. I like mostly, and this the magnitude from the huge consistency will be in newtons. So let's make it 2000 newtons. Okay, perfect. So I think that we're ready to create a job. Okay, tube 2000. Let's name it with that. Okay, a job has been created. Right click, submit. Our job has been submitted. It's running. I think that some seconds. Okay, completed. Right click results. This you can see some von Mises stresses here. You can change it to the displacements. You can see some contours from the displacements. U1 is the displacements in the x-axis direction, U2 in the y-axis direction, the vertical direction. You can see here in terms of millimeters, and U3 in the other direction. In the visualization module, in the results, we have many options for our results. We can see the limits, specify the limits. For the contour, change the contours. You can show the locations of the here of the max, of the mean. Many. You can explain them in next videos. Okay, thank you for watching.